Howdy, ladies and gentlemen. These are your electrochemistry notes. It's a specific part on galvanic and voltaic cells. So have your note packet out, and don't forget the Superstar Redox worksheet that you got last time we were in class, and it is due according to the date on the calendar. So make sure you're checking that. All right. You won't need a calculator for this set of the notes. So the interconversions of chemical and electrical energy are called electrochemical processes. So you have a blank to fill in on your notes, all of which involve the transfer of, you got it, electrons, because that's the only thing that gets to move. And this process occurs in a device called an electrochemical cell. All right, so electrochemical cells have special names, and we'll get more into details about this. So we have a blast from our past now, and you might remember the activity series of metals that we had when we did replacement reactions, single replacement reactions. And so the activity series of metals said that group 1 and 2 and Al would be able to replace hydrogen from water and from any acid. They were the most reactive. Then we had the transition elements, and the transition elements, including magnesium and aluminum, can replace hydrogen from acids only. So that was important to realize. And then hydrogen itself was a non-metal, so it didn't really get replaced. And then we had our jewelry metals at the bottom, which had the least activity. So they really didn't, most of the time, replace things. So remember, metals from lithium to sodium will replace hydrogen from water and acids. Then metals from magnesium to lead will replace hydrogen from acids only. Okay. Now we have another type of version of an activity series here, and this actually is a reduction reaction chart, and it gives the electric potentials, which are voltages that occur when this happens. So remember, we're talking about chemical and electrical processes. So those voltages are the electrical process of it, and these are the chemical processes of it. So we'll get more into how to use these numbers when we talk about batteries. Okay? So let's talk just about galvanic cells. An electrochemical cell that can convert chemical energy into electrical energy is called a voltaic or galvanic cell. These are the batteries that we use every single day. Now, the energy is produced by a spontaneous redox reaction. So you have a paste inside of here that is got an electrode, and it's got positrons, and you have an electrolyte paste, and you have things that are called like a separator, and they react with each other. And the carbon and manganese dioxide mixture will react with the zinc negative electrode, and you'll have a carbon positron electrode. And so we create a battery, and that battery has an electron flow to it. And we'll talk a little bit about that as we talk about these cells. So, flipping the page in your notes, we have the following reaction. We have lithium plus iron 3 positive is going to produce a lithium ion and a regular just iron molecule. So when we have voltaic cells, they can be separated into two half reactions or two half cells. One of these will be an oxidation that will occur, and one in which reduction will occur. So really, when we look at this, we'll look at it like we're identifying oxidation and reduction problems. So let me start with my pen. So we have 0, excuse me. So we have 0 as our oxidation number for lithium. We have a +3 for our iron, then we have a +1 for our lithium, then we have a 0 for this iron. So when we go from 0 to a +1, we are becoming more positive, which means we lost electrons, which means it was oxidized. And if we go from a +3 to a 0, that means we became less positive, which means we gained electrons, which means it was reduced. All right. Now, a half cell consists of a metal rod or strip that's immersed in a solution of its ions. Okay, so we're looking for a metal rod or strip, and it's going to be in its ions. That's going to be a key part to this. So we could say, well, the two metals that we have are lithium and iron. I'm going to go ahead and put iron on the left here, and then I'm going to put my lithium on the right. Could I have switched it around? Absolutely, but that's how I'm going to label my cell on my paper. Okay, so then remember, it's surrounded by a solution of its ions. So the ions of iron that we have are Fe3 positive, and the ions that we have of lithium are lithium positive. So we'll put those here in this solution area, and we'll put this in this solution area. So now we also need to talk a little bit about what's happening. So when we have the two half cells, they're connected with what we call a porous partition, or what we call a salt bridge. So a salt bridge is a tube that contains some sort of conducting solution. All right, most of the time that's a salt of some sort. So we're just going to label this salt bridge. Now ions are going to pass through this salt bridge to keep the charges balanced. So it can be different things, but again, it's some sort of salt that's just going to allow for the ions to pass back and forth so that they stay balanced. Now electrons actually are going to pass through an external wire that's going to be connected to the two pieces of metal themselves. Okay, so when we connect, so you'll want to draw that in from the metal strips, the iron metal strip to the lithium metal strip. And we'll have electrons, so I labeled those, are going to pass through it. Now there's a certain direction that these electrons travel. Okay. Now the metal rods in a voltaic cell are called electrodes. So this is called an electrode and this is called an electrode. And we've got them dipped down into the solutions. Now, oxidation occurs at what we call the anode, and reduction occurs at what we call the cathode. So a mnemonic to remember this is an ox and a red cat. So again, which one did we say was oxidized and which one did we say was reduced? Well, we said that Li became more positive, which means it lost electrons, which meant it was oxidized. And we had our Fe value that that metal ended up going from the Fe3 positive, and that gained electrons, which made it reduced. Okay, so the Fe3 positive was reduced, so we would label that as a cathode, because cathodes would have reduction. And if we were going to write the half reaction with that, we would just write Fe plus 3 electrons would give us just regular Fe. So we'd have Fe3 positive, cancel out the 3 positive, we'd add 3 electrons. Then for the Li, on the product side, we'd have Li positive plus 1 electron to balance that out. And that would be labeled as our anode, since that's where oxidation occurred. Remember, red cat and an ox. Those would be ways to remember this. Now, the electrons, so whatever's undergoing the reduction will receive electrons from the cathode. So we labeled the cathode here on the um, so yeah, so the lithium is going to give electrons to the um, so hold on. So the lithium ions are going to be able to work with just the lithium because we have the lithium, and then it's going to lose electrons. So those lost electrons are going to travel from the lithium over here, and they're going to go over here because the iron is going to gain the electrons when it becomes the Fe3 positive. Okay, so the direction of the electrodes is always from the anode to the cathode. So the anode, again, is, remember, where um, the value was oxidized. And so since it was oxidized, it lost electrons. And then the cathode is where it is reduced, which is going to mean actually that it gained electrons. Okay, so this is our cathode, or where our reduction occurred. And this is the anode where the oxidation occurred. So the oxidation is going to donate the electrons from here over to here. So it's going to receive them over here. And it received 3 electrons, and this gave off 1 electron. So this is the receiver, this is the giver. So in a voltaic cell, the anode is assigned as a negative charge, which should make sense because if it's excess negative, then if it's giving away negatives, then it must be negatively charged, and the electrons are always going to flow away from the negative charge. So that would make the anode would get the negative charge, and the cathode would get the positive charge because electrons want to travel to the positive end. Okay, they want to travel because the opposites will attract. So these will repel each other, and these will attract, and that's why they go in this direction. Okay, so you should have that drawing completely filled out now with positives, negatives, a salt bridge, the metal strips as the solids, and the solutions as the ions. You have it identified as cathodes and anodes. Um, Now, I do have another picture on your notes that's really just kind of showing a different reaction, and it was zinc, and then it was zinc sulfate, and then it was copper in a copper sulfate solution. So this one doesn't specifically show the salt bridge, but it does show that there is a meter here, and that's where the electrons are. So there would actually need to also be some sort of like a salt bridge right here. The reason we probably don't have that in this picture per se is because they both have this, and so they will kind of balance each other out as they transfer them because they both have these polyatomic ions in them, so as well in their solutions. But we do get these electrons or these electrical potential readings as this occurs. And this, remember, goes from the anode to the cathode. Another way to remember that besides fat cat would be to also think about it alphabetically. So you start at the anodes and then it goes to the cathodes. So it's in the alphabetical order as well. That'd be another way to think about it. So in your notes, it talks about the line notation, and it being a shorthand notation method for representing electrochemical cells. So the general form of this is to write the anode and a line and then the anode ion. Then to do a double line and then do the cathode ion, a line, and then just the cathode. Well, if we were going to do that for the example that I just showed, which was zinc, okay, then we would have zinc and the zinc positive ion. The double vertical line would represent the salt bridge, And then for a voltaic cell, we would draw it like this. Then we have the copper +2, and then the copper solid or metal. Okay, so that's kind of what I had written on the other screen right here, right when I popped it here. So this is just that notation. So we always write it as anode, anode ion, cathode, cathode. So we sandwich the ions with the anode and cathode. And again, it's done in alphabetical order. Anode, anode ion, anode, and this is cathode ion because they're sandwiched in the middle, and then cathode. All right. So if we're given the voltaic cell, so this is example 7. Okay, before we do example 7, let's talk for a minute. When only ions rather than a solid are involved in a redox process, inert electrodes such as graphite or platinum are going to end up being used. We actually can pick which one's used, but most of the time we're going to pick platinum, um, just because it's an easier metal to deal with. Graphite's kind of really soft. But I'm going to have so when I'm talking about when only ions rather than solids, if you look at the reaction in example 7, on the reactant side, it's only ions. And then in the product side, it's a solid. But since there's not a solid on both sides for us to deal with, we are going to have to pick an inert electrode. So we're going to pick platinum for our example. Okay, so that's why I wanted to make sure we talked about that. So silver is a plus. So this is a +1. This is a +2. This is a +3. And this is a 0. So the 1 to the 0 becomes less positive. So that means it gained, which means it was reduced. And this one was oxidized because it became more positive. Lost, yes. Okay, so we're going to sketch the cell on our notes. So first thing it says to do is label the electrodes. Well, since we have AG, AG is the one that is reduced. So I'm going to say that it goes with my, remember my anox and red cat. So it goes with my cathode. So I'm going to put it over here on the, if I'm going to label the anode over here for oxidation, and then I'm going to label the reduction on the other side. So that would mean I'd put my iron on the left, and I'd put my silver on the right. Okay, so I would put my solid right here if I'm labeling my electrode. So I'd put my AG here. Now, if I look at my anode, that oxidation reaction only occurs with ions. So this is where we would put our platinum. Okay, it's our electrode. We have our salt bridge, so we could just label that as well. We can label our ions. Okay. Now, we would need to draw a line from our anode to our cathode, because it always goes from alphabetical order, A to C, or fat cat, so that from the anode to the cathode. That's why it spells out fat cat, just by the way. All right, then we need to draw our salt bridge. Okay. Now we want to also do the line notation. So the line notation, remember, starts with the anode, and then the anode ions, and then the cathode ions, and then the cathode. So we would write so we would write our anode, which is PT. Then we would write our Fe2 positive and Fe3 positive, since those are both ions that would be in the solution. Then we do our double line for our salt bridge. Then we do our silver ion plus our silver. And then if we're going to do our oxidation half reaction, then really we're writing what is underneath the anode there. So we're writing our Fe2 positive yields Fe3 positive plus 1 electron. And then our reduction half reaction, we would be writing our Ag positive plus E negative to cancel that charge out, which would just equal Ag. All right. So that should finish out that part of our notes for today. And we have some things to work on from here. And otherwise, you guys catch you on the flip side.